maybe in the second session later today, we may go through some of the new material on integration. But I thought we'd look at these questions. So they're both questions about stationary points. We've got these two functions, f and g. F is x squared minus 9 times the sine of y. G of xy is x times the cosine of the product. And we'd like to investigate their stationary points. So the directions for 2, well, are the directions for question 1. Question 1 seems to imply that there are stationary points. So we want to identify them all and classify them all into one of the 3 types for each stationary point. And for each type of stationary point that we find there, maximum, minimum, or saddle point, maybe use MATLAB or a similar software to produce surface plots where we can verify that nature of the stationary point, where we actually can see a clear local maximum or minimum or saddle point, whatever. Question 2 is kind of different. That says prove that that function has no stationary points. Okay. And then question 3, just one of the practice problems in Schaum's Outline of Calculus book, which is a good source. Just a reminder, it's a good source for you to use for lots of other practice problems and examples and extra material to help with these things. Chapter 52 there, a little problem says, show that the rectangular parallelepiped of maximum volume V having fixed surfaced area S is a cube. So a parallelepiped is just a fancy schmancy word for a box, rectangular box. So it's made of straight, flat faces and right angles everywhere. But supposing it has a fixed surface area, so a fixed quantity of cardboard to make the box. Fixed number of square meters of cardboard. What's the box you can make which has the largest possible volume? So it's a kind of an optimization question. Can you optimize the volume? I mean, if you want to optimize the volume, you just make the box bigger and bigger. But if you've only got a fixed amount of material to work with, a fixed surface area, then what are the dimensions that maximize the volume? Now, intuition or experience might tell us that that will be a cube. A cube has the largest possible volume of all box shapes, given a fixed surface area. But we'd like to prove that. Question 3. Okay, so those are the things we're going to work through. So let's see if we can get it. Now, unfortunately, MATLAB isn't on this machine. I think it's frustrating because it's on the one in C014, but it isn't on here. But there's also there's various. We could try and use Sage to get a nice surface plot, or there's also this website, Wolfram Alpha. So what's the function? X squared minus 9 times sine of y. So you can try typing this function in here. X squared minus 9 times the sine of y. And maybe just ask it to plot it. So this accepts input. You can more or less type any kind of reasonable command here, and I think it attempts to interpret it. Now, it's shown us a bit of the surface there between, now what range of x? It's gone from -5 to 5 on y and maybe -4 to 4 on x. Maybe for x from -6 to 6, and for y from -10 to 10. Maybe just try and increase the range of the surface plot there. Hopefully it will. Yeah, I think it does know what I mean there. Zoom in here. Okay. So that shows you what the surface kind of looks like. And can you see any stationary points there? You see any minimums, maximums, or saddle points? Obviously, we're only looking at a finite part of the surface there, but yeah, we can certainly see lots of hills, tops of hills, and corresponding bottoms of depressions there. So there does seem to be a row of maximums and minimums going along the x = 0 line. And we also see these points to the side, which look like maybe these might be saddle points over here. So a point here, which is kind of on the, it's on the bridge between this low region here and this low region here, but it's also on the kind of saddle-y point between this high bit here, the surface, and this high bit here, the hill. So these points either side up along here and down along here, either side of the x equals 0 line, maybe there are some saddle points there. You can kind of tell a bit more precise stuff here from the contour plot, if you interpret that. But anyway, it seems like there are stationary points here. I mean, if you widen it out from, if you let x get larger and larger, well, because it's x squared, you can kind of guess what's going to happen to the function. If you make x larger and larger, it's just going to make the function go larger and larger. So I don't think any more stationary points are going to occur if you look wider. In fact, the surface plot, yeah, it just kind of, so the surface seems to be doing more extreme stuff as you get away from x equals 0. Maybe the interesting stuff is happening between about -4 and 4 with these local minimums and maximums and these saddle points. As you move away from x equals 0, you just have to have these larger and larger waves on the surface. It doesn't really look like there's other stationary points there. And of course, should I extend it in the y direction? Well, how does the function depend on y? It depends on it through sine. But of course, the sine function is a periodic function. So if I look at larger and larger intervals of the y variable, I'm just going to see the same thing happening. So this behavior here, which we see in this portion of the surface, that's probably just going to be repeated infinitely along the x equals 0 line, okay? Because as you take larger and larger values of y outside of, oh, I meant to increase the x there, sorry. Outside of y from -30 to 30, say, we'll just see more and more of these waves or cycles on the surface. So we should just see more and more of the same stuff. Okay, but that investigation anyway shows us kind of what to expect. You know, it's kind of harder to see the detail there when we zoomed out too much. But we expect to see a row of minimums and maximums and saddle points going up either side of it. Okay, so let's see if we can identify those. If we can identify those algebraically. Oh, already. Let's turn this thing on. So we've got our function x squared minus 9 times the sine of y. This is our function f. And so what's the definition of a stationary point? The stationary points are the solutions to, are the points x, y that make both partial derivatives vanish. Okay, so let's just state that clearly. The stationary points x, y are the solutions, or maybe to emphasize it, the simultaneous solutions. I think I missed out an e there. Simultaneous solutions to the two partial derivatives equal to 0. So we have to solve a simultaneous system of simultaneous equations, pair of equations. So let's go ahead and try and find those equations, i.e., so what's df dx? We're differentiating f with respect to x. It should be becoming quite automatic now for you. You differentiate it with respect to x, you treat any other variables as if they were constants. So this sine of y, that's just acting like a fixed constant. So it's a constant multiplied by the polynomial x squared minus 9. So that's going to have the derivative 2x times whatever that constant value is. So you're going to be looking at this equation equal to 0. And the y derivative, well, you're differentiating with respect to y. You treat anything involving x as a fixed constant. Indeed, the 9 is a fixed constant. So what we see is just some fixed constant multiplied by sine. Well, that's going to have the derivative x squared minus 9 times whatever the derivative of cosine of y is with respect to y. Sorry, of sine is. So that gives you cosine of y. Okay, well, those two equations look fairly approachable because they're both presented in factorized form. And it's quite clean because they're presented as factors and each factor relies on just one of the variables. So, you know, it looks quite approachable. So it shouldn't be too much problem here. Maybe just label these. So let's look at the solutions to A first. So we're looking for simultaneous solutions. What we're going to do is solve one of the equations and then feed those solutions into the other one, or apply the solutions of A onto B, or insist that A, whatever comes out of A, insist that that be true for B, and ultimately try and find these simultaneous solutions x, y. So what do we see in A? Well, in A, we see that the derivative is equal to 0 if and only if. So what are the conditions? Well, certainly if x is 0, that's going to give you a solution, but also if sine of y is equal to 0. So if and only if x is 0 or sine of y is 0. Well, make that a bit more precise. When is sine of y 0? Sine of y is 0 whenever y is an integer multiple of pi for some n and z. Those are all zeros of sine, and they are exactly all the zeros. So these two conditions, x equals 0 or y equals n times pi, they capture all the solutions of A. Okay. So now we want to take those and transfer them onto B. So now look at B. Look at B under these conditions. These conditions, namely these ones up here. Well, only one of these has to be true. X equals 0 or y equals n pi. So we'll treat both of them kind of separately. If x is equal to 0, then df dy is equal to 0 if and only if, well, if the x is 0, then this simplifies to minus 9 times the cosine of y equals 0. Well, that's 0 only when, I mean, the zeros of minus 9 times the cosine of y are exactly the zeros of cosine of y. When is cosine 0? Cosine is 0 whenever you have an angle which is like pi over 2 or 3 pi over 2. Okay, so we need an odd multiple, some odd multiple of pi over 2 for some n and z. So these numbers, 2n plus 1 pi over 2, if n is any integer, well, what we're looking at is an odd multiple of pi over 2. So if you think about the unit circle, the complex plane, which gives you your cosines and sines, these odd multiples of pi over 2 means you're at an angle, your point is on the y-axis, either at plus 1 or minus 1. So the cosine, the x-coordinate is 0. On the other hand, so that's the x equals 0 case. What if y is n pi? If y is equal to n pi, then df dy is equal to 0 if and only if. Well, what does it look like then? So you look at df dy. If y is n pi, so y is some integer multiple of pi. That means the cosine value Well, it might be +1, it might be -1, depending on whether the integer multiple is odd or even. Well, we don't have to track that exactly because remember, we're looking for zeros of all this. So the df dy will be equal to 0 if and only if the x squared minus 9 part is equal to 0. The cosine will just multiply it by plus or minus 1. So that won't, that won't affect whether it's equal to 0 or not. It just depends on whether the x squared minus 9 factor is equal to 0. Well, that's easily understood. When is x squared minus 9 equals 0? When x is plus or negative 3. So what have we got there? Stationary points, remember, are where both partial derivatives vanish. So we're looking to identify points, and by point we mean a pair of values, x and y. We're looking to identify those pairs which make both of these equations true simultaneously. The first equation is true under these conditions. X equals 0 or y equals n pi. So one of these has to hold true to have a simultaneous solution. If it's the x equals 0 one, then for the b to be true, we must have y satisfying this. If we're looking at the y equals n pi, half of the solutions of A, in order for a simultaneous solution to hold, in order for df dy to be equal to 0, we must have x being plus or minus 3. So we have these two families of stationary points. Okay? Two families of stationary points characterized like this. So you need to carefully identify the logic and carefully identify what are the situations when both of the equations are true. What you don't want to do is start pairing this with this or pairing this with this. I mean, they're actually, well, they're not exactly contradictory. Well, these two are contradictory. Those two are contradictory. But, the way the logic has come down is that we have a simultaneous solution if these two conditions are true, these two red boxes, or these two red boxes. Okay. So we can summarize that now and say the stationary points are xy equal to, so you can have 0, 2n plus 1 times pi over 2 for any integer n. And the points x, y, which are x can be plus or minus 3, and the y bit can be n times pi. Again, for any n, an element of z. Okay, this is what we seem to have identified. We can do a quick check. Just look back at the plot. Does that tally with what we found in the plot? Yeah, it kind of does. Oops, yes, it kind of does. These ones, when x is 0 and y is some odd multiple of pi over 2, well, those are those ones that we can see. Those are the hills and dips that go along the x equals 0 line. And these ones, plus or minus 3 n over pi, well, that's two rows, one at plus 3 and one at minus 3. And those seem to be the two rows of saddle points going along. The one at x equals plus 3 about here, so it's this row of points along the surface, and the ones at x equals minus 3, which is this row of points along here. So this certainly agrees with the look of the surface. We can say. It's not a formal verification because we're just going by how the surface appears. I mean, the the maximums and minimums are fairly clear. The stationary points may be a bit harder to precisely say where they are, but certainly seems to be in agreement. So now we want to classify them. So now we wish to classify all these. So we need to, i.e., evaluate the Hessian determinant D, which is this product of second order partial derivatives minus the square of the mixed Okay, this is this quantity which determines the nature of the stationary point. Well, yeah, let's just put it down. It's the function. I mean, if the functions were a bit overly complicated, I might separately evaluate each of these parts, because otherwise you'd have a massive, too long expression. But I think that things are relatively simple. So, I mean, d2f dx squared is going to be 2 times sine of y. The d2f dy squared is going to be minus x squared minus 9 sine of y. It's not too bad. And the mixed second order partial derivative is going to be 2x cosine of y. So that's your D. What can we do with that? Well, if what we saw on the surface was right, it should be that all these points are saddle points. So maybe we can do that quite cleanly. So we can evaluate the D at plus or minus 3 n pi. Maybe we can just do it all at once. What do you get when you stick in n pi? Well, when you stick in n pi, sine of an integer multiple of pi is always 0. So the first factor is 0. So it doesn't matter what that is. In fact, it's going to be 0 again. And here you get something non-zero. What you get plus or minus 6. And cosine of n pi is plus or minus 1. Yeah. But then it all gets squared. So the ambiguity over signs here is rubbed out. The ambiguity is rubbed out. This is always 36. So it's always negative 36. So it's always strictly less than 0. Yeah. So it's strictly less than 0. And according to the classification, if D comes out strictly less than 0, we've got a saddle point. So the points plus or minus 3 n pi are all saddles. I mean, what were we using there? What justification, or, you know, don't need to say anymore. The justification we're using there is that cosine of an n pi is always plus or minus 1, and sine of an n pi is always 0. Just the facts that we're going in. That's okay. Then the other ones, D at 0, and now we got a 2n plus 1 pi over 2. What does this look like? So x is 0. So anywhere you see an x, just forget about it. So we see an x here. So we just forget about all that. See an x there. Well, okay, forget about the x squared part. So it seems to be, so you get a 2 and a plus 9. So we seem to get an 18 times the sine squared of 2n plus 1 pi over 2. Now, sine of an odd multiple of pi over 2, that's either plus or minus 1. Sine of an odd multiple of pi over 2 is plus or minus 1, but then it just gets squared. So that is just 18, which is bigger than 0. So we're using the fact that sine of an odd multiple of pi over 2 is plus or minus 1. So when the Hessian determinant D comes out as positive, the classification of the point is given by looking at one of these second-order partial derivatives and examining its sign. So we need the d2f dx squared evaluated at 0, 2n plus 1 times pi over 2. So that is this quantity here. Well, it's 2 times it. Yes, so this comes down to the odd or evenness of n. It's equal to it's going to be plus 2 or minus 2. So it's going to be plus 2 when n is even. And whenever n is odd, you're going to be at the minus 2. So it's just tracking what happens to sine of those odd multiples of pi over 2. It depends on whether n is even or odd. Okay. So the point 0, 2n plus 1 over pi over 2 is a local maximum when n is odd, and a minimum, a local minimum, when n is even. So that's nice. You have a nice classification of it depending on the parity of that parameter n. So if we focus in on any of these points, let's say we focus in on one of the saddles, just to observe this. So at plus or minus 3, so let's focus in on x equals 3. So let's just go a little bit either side of 3. So go from x equals 2 to 4. And we want to go either side on the y-axis, either side of an integer multiple of pi. Well, let's just go either side of 0. 0 is n times 0 is 0 times pi. So let's just go minus 1 to 1. So this, we should be seeing a saddle point here. So we're centering the plot on does that look like a saddle point? Yeah, so the center of this surface right here, you can see if you go in this direction or back in this direction, this point is acting like a maximum. Whereas if you go to this corner or to this corner, the point is acting like a minimum. Maybe if we'd widen the limits there, still kept them centered on the point 3, 0, but if we widen the limits, we might see it slightly more pronounced. Let's go from 1 to 5, maybe minus 2 to 2. You should see that saddle point nature be slightly more pronounced there, I think. And then we can center it on one of the other points, try a couple of them, and observe the local maximum and local minimum. Okay. So if we go slightly either side of 0, so let's try -1 to 1 on the x, and on the y we want to go slightly either side of pi over 2, say. So this is n even, so this should be a local minimum. So we'll go pi over 2 minus a half to pi over 2 plus a half. Okay, so I've gone too complicated for it there. But just go, so it's what's pi over 2? That 1.5. So go from 1 to 2. So this should look like a local minimum, and indeed it does. Okay, I've only roughly centered it on y equals pi over 2. Pi over 2 is somewhere between y equals 1 and y equals 2. So that clearly looks like a local minimum. Okay. And if you went to one of the ones corresponding to n odd, we would see a local maximum as well. Okay. Okay. Any questions about that? Any clarification you'd like? I'd say the most difficult part of it, though, was identifying the stationary parts correctly and just following this logic through, and be sure to describe them all, that you're capturing them all and that you're not declaring that some are stationary points that aren't stationary points. Second question there. Okay, this should be shorter, showing that this function g of xy has no stationary points. And we could try looking at the graph. But perhaps we shouldn't be seeing any stationary points on this. Well, the surface goes up and down a lot because of the cosine factor, but there's nowhere there which clearly looks like a local maximum or a minimum. There are ridges. There are lines where the surface falls away either side, but those lines aren't flat. Those lines themselves are on increasing or decreasing arcs. So there's no stationary points immediately apparent. Okay. So we consider the two partial derivatives. Now dg dx is perhaps the harder one because there we need the product rule. So this is going to be cosine of xy plus minus xy times the sine of xy. And this being equal to 0. That's using the product rule and x times the cosine of xy. dg dy should be simpler because there's no product stuff going on involving two different factors depending on y. So it's just minus x squared times the sine of xy. So we're looking for solutions of these. We're looking for simultaneous solutions of these. We should follow the same procedure as last time, solve one of them, or at least, well, when I say solve one of them, I mean describe clearly the conditions under which one of them is true, and then impose those conditions on the other one. But we should do the easier one first, or we should do the one that gives us the clearer description, or the clearest conditions. Now, which of these looks the easiest in terms of describing when it's equal to 0? Well, you see, one is a difference between two complicated functions of x and y, you could say, whereas the other one is a product of factors. Now, products of factors are much more amenable to deciding when they're 0, because products are 0 if and only if one of the factors is 0. Difference is 0 when this is equal to this, and well, that looks more complicated to judge directly. So B is easier to analyze. So we'll analyze B. dg dy is equal to 0 if and only if, well, if x is 0, that bit of it is 0, it's going to be 0, or if the other bit, or sine of xy is 0. When is sine of xy equals 0? Well, we know when sine is 0. Sine is 0 at integer multiples of pi. So that's true only when xy is an integer multiple of pi. And in fact, the second case includes the first case. If x is 0, then that fits in with this, because this is the case where x times y is equal to 0 times pi. So actually, this boils down to just this condition here. So x times y must be an integer multiple of pi in order for equation B to be true. So then you put this into the other equation. Yeah, because we're looking for simultaneous solutions. These are the situations when equation B is true. Now, we're not getting any particular unique points here. These are xy equals n over pi. That's a whole family of curves in the plane. It's like a whole family of kind of hyperbolas in the plane. But so we applied this condition, or these conditions, because it's for n, any integer, so I guess it's a family of conditions. Apply these conditions to A to see that if xy is equal to n pi, then dg dx is equal to 0 if and only if so you just apply this condition. Xy is an integer multiple of pi. Well, that will go in fairly easily, because you're just going to put it into cosine and into sine, and they behave well on integer multiples of pi. So if and only if cosine of n pi minus n pi sine of n pi equals 0, now what's cosine of n pi? An easier way to describe cosine of n pi. Hey, it's too much chatter there. Some annoyed people, including me. Cosine of n pi, that behaves as plus or minus 1. Sine of n pi, sine of an integer multiple pi, well, that's always 0. So what do you make of that? Plus or minus 1 equals 0. You say, well, Killian's obviously made a mistake. Plus or minus 1 is not equal to 0. Well, I'm not claiming it is. That's not what I'm saying. I'm saying, I should have written it down, but up at the top, I mean, I wrote it down at the start of the other one. Up at the top, it should say xy is a stationary point if and only if, and then right down at the bottom, we've got plus or minus 1 equals 0. Well, that's never true. It's nonsense. So it's nonsense to say that xy is a stationary point. So there are no stationary points of this function, okay? Because we seem to be saying xy is a stationary point. You could put at the top just to make the logic clear. If and only if. So this is the start of the sentence. And then you have a whole lot of mucking about in the middle of the sentence, but the sentence ends plus or minus 1 equals 0. So it's a stationary point if and only if. Nonsense. So it can't be a stationary point. So this shows that G has no stationary points. Okay. Okay, but you still see the need for careful argument. You still need to approach the two partial derivatives equal to 0. Approach that carefully, because each equation on its own has plenty of solutions. You know, both A and B have plenty of solutions of their own, but it's just that they don't share any solutions. There aren't any simultaneous solutions. Okay? So that means there's nowhere on the surface which is completely level, where the tangent plane is completely level. The surface is always increasing or decreasing in some direction at every point. Okay. All right, then. That's where we're going to end for the moment. And I shall see you all for some more excitement in an hour.